Okay, hello everyone, and welcome to our workshop on using Earth observation for water quality monitoring. And thank you very much for joining us today. As Paula has said before, if you're just joining, this workshop is being recorded, just so you are aware. My name is Emily Sim, and I am a marine data specialist and ecosystem analyst at the Joint Nature Conservation Committee, JNCC, and I will be your chair for the first day of the workshop today. For those of you who are not familiar with JNCC, we are the public body that advises UK government and devolved administrations on UK-wide and international nature conservation. This workshop is being delivered under JNCC's Copernicus project, which is funded by the Caroline Herschel Framework Partnership Agreement on the uptake of Copernicus data. The agreement was set up in 2018 with the aims of increasing the uptake of Copernicus data, products and services. Our project at JNCC is specifically aiming to increase the use of Copernicus data and services across the UK and enable the delivery of public environmental functions more efficiently or effectively across multiple policy areas. We're achieving this by working with partners to deliver a set of work packages, which is including capacity building and training, collaborative research and development to support new practical applications, and delivering events such as this workshop over the next 2 days. So the aim of this workshop is to raise awareness of how Earth observation can be used for water quality monitoring in freshwater, estuarine and marine environments, and there is a specific focus on supporting environmental policy requirements. We have a fantastic range of talks over the next 2 days to showcase innovative and policy relevant applications. We hope that these will inspire you to think about new ways that you could use Earth observation in your work or studies. In case you haven't already accessed them, there are resources about the workshop available to download from our website, and they are also on the Eventbrite page. Paula has posted a link to the chat function in GoToMeeting, so you can find them there as well. If you follow the link, you can download the workshop programme, information on how to participate, and a selection of useful links to information about using Earth observation for water quality monitoring. So just to start, we have some housekeeping before we go any further, just to help the workshop run as smoothly as possible. So this session, as we've mentioned, is being recorded, but attendees will not be visible in the recording. The videos and slides will be made publicly available on our website after the workshop. This is likely to be next week, and we will inform you when they are available. As we go through, please follow these simple guidelines. Keep your microphone muted and your webcam off. Only use the chat function in GoToMeeting for technical issues. So if you go to your GoToMeeting panel of controls, it's the one with the little speech bubble icon. So any technical issues, just post them in there and we will try to help. We are going to be using Meeting Pulse to ask the speakers questions, and I'll give some more information on that in just a second. And please be polite, positive and constructive in your questions and comments. If you're a Twitter user, feel free to use the JNCC_EO for water hashtag and tag at JNCC UK. Your feedback is really important to us because it helps inform future workshops that we're going to run. Please fill in the form at the end of the event, and all the feedback is anonymous. You'll get a link to the survey at the end of the day via an email from Eventbrite. So this is what today's agenda looks like. In the first session, our keynote speakers, Christine Maggs and Carsten Brockman, will set the scene by giving an overview of the environmental and policy context for water quality monitoring and the sensors, data and products available. We then have 2 sessions giving examples of a wide range of policy relevant marine applications, from detecting plastic pollution all the way through to harmful algal blooms. As you can see, there is time allocated at the end of each group of talks where the speakers will be happy to take questions from the audience. You can ask questions at any point during the workshop, and I'm just going to take you through how you can do that. So we are using Meeting Pulse, as is on my screen, to manage our questions as we go through the next 2 days. This is now open and live, and you can join it if you haven't already via the links that have been posted and the information you've already received. To ask questions or to see what questions have already been asked, click the QA icon at the bottom of the page. If you'd like to submit a new question, you can click the green Submit New Question banner, type in your question and click Enter. Please make it clear which speaker your question is for, and all of the questions are asked anonymously. Final point, if you like other people's questions and you want to hear them answered, then please upvote them by ticking on the triangle on the left-hand side of the question. We will read out all questions to the speakers during the Q&A sessions, and we'll try to get through them all, but we'll be starting with those that have the most votes. A key aim of this workshop is to increase the use of Copernicus data and products to support environmental policy. Tomorrow, we have a session introduced by the DEFRA Earth Observation Centre of Excellence entitled Innovation Through to Impact, Linking Policy Priorities to Research and Development. In this session, our panel of experts will discuss suggestions submitted by you, the audience, on two key questions. The first one being, what are the priority water quality monitoring applications to meet UK and EU policy requirements? And the second is, what research and development is needed to make these applications operational? We are very keen to get as many of your suggestions as possible on this and make it as interactive as it can be. You can post your suggestions at any point over the next 2 days. Any we don't manage to deal with in tomorrow's session will still form part of the workshop report and any future discussions that we have. You can use Meeting Pulse to submit your suggestions for the discussion, and I'll just show you how to do that now. So coming back into Meeting Pulse, you now want to click on the ideas icon at the bottom of the page, which is the little light bulb on the bottom left-hand side. Then if you click on the question at the top of the page, that will bring up the suggestions that have been made so far and the opportunity to submit your own suggestion. If you click the yellow Submit Your Suggestions banner, type in your suggestion and press Enter. As with the questions, suggestions are completely anonymous. However, you could mention your organisation's name if it's relevant to your suggestion. As before, please upvote any suggestions that you would like to see discussed by our panel. So without further ado, we're now ready to start the first session, and I'm going to hand over to Professor Christine Maggs from JNCC to give the first talk of the workshop. A very warm welcome to yourself, Christine.
Well, I'd like to say welcome to everyone who's online already. Thank you very much for joining JNCC for this conference. And I'd like to thank Emily for introducing this and Paula for inviting me to speak. I've looked through the programme, extremely excited at all the interesting work that's going to be discussed today and tomorrow, and I'll join as many of the sessions as I can. I can see there's already 230 people registered, which is fantastic. You're not all online just yet. Fantastic range of countries that are attending and institutions, both in UK, Europe, and more widely around the world. So obviously we're all suffering tremendously from this COVID-19 pandemic, but there are one or two benefits, and our Copernicus conference series is one of those benefits, because we have been able to host more people than would have ever been able to come in person. So although there's a great deal to be sorry for, we have a few things to thank the pandemic for. So as it says here, I'm Christine Maggs. I'm the Chief Scientist of JNCC, and I try to have a broad understanding of all the work we do, and a lot of the very exciting work that we do centres around remote sensing and Earth observations. So I'm to talk to you or discuss the environmental context and why marine and freshwater environments are particularly important in terms of conservation and monitoring. So some aspects of this, biodiversity, obviously there's extremely high biodiversity in aquatic environments. I've just given a picture here of three marine environments in the deep sea. Of course, aquatic freshwater biodiversity is equally important and impressive. The ecosystem services and natural capital need to be monitored, so we need to be aware of our needs and our resources in terms of offshore energy, food security and recreation. We all depend on aquatic ecosystems. So the sorts of natural capital projects in the marine environment that require remote sensing, we have been working, the JNCC has a particular interest in this because we work in the overseas territories of the UK. So we work in the Caribbean and the South Atlantic, helping to assess natural capital and getting the value of things like coral reefs to help protect against hurricanes and storm surges, natural disasters that can impact on economies. And we use the environmental evidence to advise economic policy making and infrastructure planning. All of these drawing on data from remote sensing. So the natural capital of the marine environment is extraordinarily high. Some people don't believe the values that are produced by scaling up how many sewage plants it would take to do what the water does naturally and so on. And we're all aware of the big push for energy from the offshore environment at the moment. So there's a lot of both pressures, as we call it, on the ocean, but also a lot of value from the natural capital. So those are some examples of what goes on at sea, oil rigs and so on. And I just wanted to mention a couple of examples of threats to the ecosystems and ones in which remote sensing is directly involved. So I'm going to mention to you a project which this is what's called a green tide in a bay in Ireland, where the mud goes green because of what's described here as foul-smelling green algae in rich tides. The green algae build up due to eutrophication, too many nutrients, often to do with farming wastes inappropriately disposed of. And these can be detected from space and they can be monitored. So any effects of interventions in the agricultural wastewater processes can be revealed by remote sensing. So I'm giving you some examples here from a project that I'm actually an external evaluator of. It's not a JNCC project, it's in the NUI of Galway. And they, here is some the remote sensing that they've been using to study these green tides over time. And their old satellite photos, the Landsat, are very poor resolution, very big pixels, 2010, 2013, and they're studying the area of these green tides. And then over time, they're using Planet, which is gives a better resolution, also shows the distribution of the deep green tides, 2016. And now they're using Sentinel 2, and their resolution has greatly improved. So the policy context within which we work, JNCC is very much working at the policy science interface. So we need to be very much aware of the relevant legislation and the policy that's required for water monitoring, and that brings both our UK waters, but also the overseas territories are part of our remit. This is the famous horrendogram produced by Mike Elliott in Hull. I don't know if Mike's online, but he loves this picture. This shows all of the different conventions within the UK, within Europe, and all the kinds of processes. There is a key up here which shows that the blue squares are international conventions. There are EU directives here in red. There are UK primary acts of parliament around the outside here, and so on. So the herendogram covers the very large number of conventions, legislation, and so on that we all have to respond to. And I think without using remote sensing options now, it would really be impossible to get the data that is needed for responding to all of these. And some of these are at different scales. So we've got European directives such as the Marine Strategy Framework Directive, Habitats and Birds directives. The UK, as most people will be aware, is the transition period for leaving the European Union ends shortly, and this stuff has to be transposed into our own domestic legislation now. So the national legislation is covered here, but we also respond and collaborate and indeed report on a lot of the international requirements, such as the OSPAR, which is and conventions on biological diversity. So there's a very large number of drivers, of directives, and of our work at different scales. And one area of what we do that is of particular importance to JNCC, we in fact have led in the offshore waters, is marine protected areas designation, management, and monitoring. And the UK waters are large, particularly up the Faroes Shetland Channel. So these little areas here, lasso areas, cover all of the marine protected areas that have been designated, and we've just reported a new enormous one off the coast of the western coast of Scotland. So to do this has mostly been involving using literature published by other people, offshore surveys, and so on. But I see that some of the satellite data that's now available that wasn't perhaps available in the past can help to understand things like water quality in those areas. And of course, we use the monitoring of ships using satellites as well. So marine spatial planning is how the JNCC advises alongside the MMO, Marine Management Organization, licensing and regulation of various activities that govern where resources will be sustainably exploited and where they won't be, should there be some completely exclusive marine protected areas. And these require important maps, such as the habitat maps made by the UK CMAP to underpin all the above work. So this is UK CMAP, and there's a lot of areas that is still not fully understood as to what exactly is on the bottom. And this is a great hindrance to producing natural capital assets registers, because we don't know what actually is going on in some of those areas. So challenges of water quality monitoring, the kinds of challenges, well, it's enormous. The sea is really big. This is an example going back to the macroalgal blooms using satellites again. So if we were to try to call in at all of these shores and find out how much green macroalgal blooms is, the scale along European coasts is just far too big to be visited, far too big for people to call in at. So the sheer size of the intertidal areas, but also the depth of the deep sea, means that without using remote sensing, it's impossible to gather enough data. The areas are truly gigantic, as I said, and a lot of the work can now be done from space. We still need to go undersea, And we are, in fact, JNCC has had a project helping DEFRA to evaluate autonomous underwater vehicles, which will be the equivalent for the equivalent of satellites, but for actually deep undersea. So this is remote sensing in the undersea environment. And the vision of the future in that, of course, is that there will be no more big ships like the new Attenborough vessel, but instead we'll just send out fleets of marine aquatic drones. Problems other than the size, scale, depth, and inaccessibility of the marine environment, it's very dynamic. To get information in real time, surveys can only give you a snapshot in time. We need the integration that comes from remote sensing. There may be some, this conference may find that there are some synergies between the way that things are done in freshwater and the way that they're done in the marine. And we also need a real-time tracking of events such as oil spills in the same way as on land. We need to be able to see when peat is burning at sea. We need to see where oil has gone and other events such as that, and indeed tracking features such as the great plastic island in the Pacific. So I'll stop at that and hand back to Emily for the next presentation. And thank you very much for your attention.
Brilliant. Thank you very much, Christine. Very informative introduction. Thank you very much. We are now going to move on to our next talk. If you do have any questions for Christine, please feel free to put them into Meeting Pulse anytime during the workshop, and we will answer them when we have our question session after the next talk. So it now gives me great pleasure to introduce Karsten Brockmann, who is going to take us through Copernicus sensors, data, and products. Welcome, Karsten.
Yes, good afternoon, everyone, and thank you, Paula and Emily, for inviting me and giving me the chance to talk about Copernicus sensors, data, and data products. My name is Karsten Brockmann. I'm the managing director of Brockmann Consult, which is a private company located in Germany. We are providing services connected with environmental data. So we are giving consultancy, we are developing software and delivering information products. We do this since a while, and our customers are local authorities dealing with monitoring of our environment, and particularly the water environment, being this inland waters and coastal waters. We are working also with a lot of colleagues from the UK in R&D projects, and when I looked at the agenda, many of the talks coming, I think I have a vague idea of what's being said, and we are working with these colleagues together. So once again, thank you for inviting me and giving me the chance to give this presentation to you. I forgot to say, my background is physical oceanographer, and I started to work on optical remote sensing during my studies already. So Copernicus, to start kind of top down, is the European Earth Observation Program. Sorry if some of you already know this, but looking at the broad audience of about 230 people, I know that half of you know it, the other one doesn't know it, and I want to take everyone on board. So it's a European Earth observation system led by the European Union and executed together with the European Space Agency, as we will see in a minute. It has a big ambition. It's Europeans' response to global needs to manage the environment, to mitigate the effects of climate change, to ensure civil security, and of course to support all the national and international legislations and international conventions, as we have just seen in the talk given by Christine before. The idea with Copernicus is to have a system in place composed of a space segment and service segment which is giving us a global view on our Earth. And this includes the marine environment and the land environment with the chlorophyll and phytoplankton in the water, as we can see, but also the vegetation on land. It gives us information on the oceans like sea level height, sea surface temperature, on land additional information on soil moisture, and when we go to the atmosphere, trace house gases, carbon dioxide, and NO2, and other trace gases. So it's really the attempt to have a complete, as much as possible, as much as can be done by satellites, view on environmentally relevant parameters. This is all done in order on the big picture to support the global agendas, and in particular to name here are the SDGs, this Sustainable Development Goals, and again combining these different types of information for smart decision making, for food security and other aspects. Likewise, to support the UNFCCC climate action through the Paris Agreement. And here we will see later how important it is to get long-term consistent records of essential climate variables, and to support disaster risk reduction as it is agreed in the Sendai Agreement. And here giving high spatial resolution, providing key information on infrastructure, and to be able to react in a rapid response manner. But beside this global agenda, there is, of course, also the European legislation and national legislation. And as we heard now, I mean, as we all know, the European EU legislation, the relevant for the water, and like all others, will be in some way transferred into UK national rules. We have the Water Framework Directive on the very left side, which is, I think, known to many of us. We have on the broader scale, the Coastal and Oceanic Waters, the Marine Strategy Framework Directive. And then we have on the small scale also the Bathing Water Directive. And thanks, Christine, for also mentioning the Habitats and Birds Directive or the Natura 2000 directives, which is also quite relevant and where Copernicus can provide us a lot of information to this. So how is it implemented? How is it organized? As I mentioned in the initial sentences, it is a European program, let's say organized by the European Commission, which has the overall program coordination. And then it is split into basically two main components. We have the space component or the space segment, which is delegated to the European Space Agency. And we have the services component, which is again coordinated by the European Commission, but here it is delegated to certain entities. For example, the European Center for Medium Range Weather Forecast, ECMWF, for the climate and the atmosphere, and Mercator Ocean International for the oceans, and others. I will go into some detail on both sides, the space component as well as the services component. Very important is the sentence at the bottom. In situ data are supporting the space and services component. It's really very important, in particular for the case of water quality, that the satellite data need to be complemented by in situ data, or you can also say the other way around. The in situ data are complemented by the spaceborne data. You can use it ideally in combination, starting from deriving algorithms down to validating and finally combining it to give you the full picture of the what you're interested in. Okay, so I will first touch upon the space component and then the services component. So on the space component, Copernicus in its current definition is composed of 6 Copernicus missions, the satellites and the corresponding scenarios. We have Sentinel, and these dots actually mean how many of those are currently active. The radar satellite Sentinel-1, 2 in space. Sentinel-2 is a high spatial resolution optical mission. We have 2 in space, and this will be important for the rest of my talk. Likewise, Sentinel-3 2 in space, Sentinel-5. P is currently in space as a precursor for the final Sentinel-5, 4, and 6. Just to give you, and that you can take notes if you wish, here is again the explanation. So Sentinel-1, the SAR imaging satellite, is dedicated to many applications, but very important also for marine applications to give us physical quantities like wind and waves. We have the Sentinel-2 multispectral imaging instrument. It is dedicated still for land applications as listed here on the official slides, but practically it's quite important and heavily used also for water applications, in particular for inland waters. Sentinel-3 is also called the Blue Sentinel, which is dedicated to ocean and global land monitoring, but actually mostly used for ocean monitoring. And it has a suite of instruments on it giving ocean color information, what is relevant for this talk, but also on sea surface temperature and sea level height for the altimetry. Sentinel-4 is a geostationary instrument giving us atmospheric composition trace gases. Sentinel-5, precursor, and later on the polar orbiting, is also dedicated to atmospheric composition. And then Sentinel-6, which is a follow-on of an existing altimetry mission, also very important for physical oceanography. So that's the current suite. And this is what, let's say, Europe has committed to launch and to operate. Each of these little rounded rectangles is one satellite. Each of these missions is composed of at least 4 satellites. 2 are operated in parallel, Sentinel-1, 2, and 3. We have the 2 in space since a couple of years already, which is giving us high frequency of the observations. And the same type of satellites and instrument is already ready built. It's parked in the garage and ready to be launched is one of these fails. And actually what's currently being discussed is to launch the C model of the satellites, not only when the nominal end of the lifetime has reached, but maybe before, to have a constellation of 3 satellites in space being operated at the same time. This is thanks to the high funding which was given in the last funding range for Copernicus, where actually member states paid more than what was asked for, and this is currently being discussed to launch the C satellites and then to have a constellation of 3. At least I know this for Sentinel-3. Actually, I'm not sure if this also applies to the other ones. All right, so 5P is also in space, and the other ones are coming in the next years. What is very often not, let's say, mentioned or sometimes forgotten is that the Copernicus program is not only the satellite Sentinel, the Sentinel satellites, but also the contributing missions. So these are national missions like DIMOS, or private ones like Rapid Eye, for example. And these missions, they provide a certain contingent, which is paid by the European Union and then made available for users of the Copernicus program. So this is the contributing missions, which can be used for the applications as needed. Now, the Sentinels which are currently operated is shared to some extent between European Space Agency ESA and the European Meteorological Satellites Organization, EUMETSAT. ESA is responsible for Sentinels 1, 2, and 3, the land part of Sentinel-3, and EUMETSAT Sentinel-3, the marine and atmosphere parts, and then Sentinels 4, 5, and 6. And I can just recommend to go to these websites. You find a lot of information there. In particular, for Sentinel-2, you have all the background information, likewise for Sentinel-3, and you have these regular mission status reports where you find up-to-date information. They're issued every month. What is the status of the missions? Where are products? What are problems? What are things that have been resolved? And where are other things that are coming in the future? And the same is done by EUMETSAT for their Sentinels. For example, the Sentinel-3 product release note on the ocean color products you find there from EUMETSAT. And since Sentinel-3 is a mission which is shared between ESA and EUMETSAT, you also find the level 1 product release node on both sides. So that's just to know that this Copernicus space is a bit shared between ESA and EUMETSAT. Going a bit more detail on the data which are relevant for water quality coming from the Sentinel satellites. These are the products as they are generated by the ground segment, which belongs actually to the space component. But this is happening with the data on ground. So it's still ESA EUMETSAT doing this. Sentinel-2, the standard products which are prepared are top of atmosphere reflectances. So the sunlight reflected back from the water in 12 spectral bands with quite narrow to very broad bands and spatial resolution between 10 and 60 meters. And this is covering all inland waters and all coastal areas. Sentinel-2 has a level 2 product. I will explain these levels a little bit later. Just for those who already know this, this adds, let's say, information and is deriving surface properties. And these level 2 products for Sentinel-2 are dedicated to land, with those which are provided by the ground segment. So there is no level 2 product for water applications. These are today provided by downstream service providers and by the Copernicus services. I should have mentioned this on this slide. It's a bit different for Sentinel-3, where the level 1 data, which are measured by the satellites, you can see here the differences already. We have much more emphasis on the spectral characteristics, 21 different spectral bands and more narrow bandwidth. On the contrary, of course, a spatial resolution of 300 meters, and then we have global coverage. And we have their dedicated level 2 products, which are useful for water quality applications. It also comes with a scene classification. It has a water leaving reflectance calculated with a dedicated processing system, which is actually very good for ocean and coastal waters, but not suitable today for inland waters, but space agencies are working on it. It provides chlorophyll and suspended matter standard products, yellow substance absorption, attenuation coefficient, and actually more is under preparation by EUMETSAT. So just to give you some images after so many text slides, this is a Sentinel-2 image, top of atmosphere, just true color composite of how it looks like, of the Danube Delta. And that's basically what you get, of course, numbers, and you can calculate stuff out of this. The things you can calculate, as I said, are not done by the ground segment, but by downstream applications and Copernicus services. So things you have to do is a cloud masking, adding a cloud masking, then doing an atmospheric correction, and then eventually calculating a chlorophyll concentration, as it is done here, color coded. If it's red, it's high chlorophyll concentration. If it's blue, it's low. This is how it looks like from Sentinel-3, a product example. Sorry, I'm just checking the chat if someone wants to tell me. Okay, water product example. So you can see here, it's measured in very long stripes from one pole to the other pole, actually, where you have light. And then it's cut into more handy pieces, but covering a much larger area of 2,000 kilometers, as you can see here. And this is a nice example of the North Sea with the UK and Germany. So both, I'm from Germany, as you can hear, is covered. And then this is the standard product as it comes from the ground segment with the chlorophyll concentration, a similar color coding as before. Click. So I mentioned these processing levels already, and I would now explain to you this a little bit better, and then we can see what is the space segment or the space component and the services. We have the level 0 data. This is what is really measured by the satellite in raw data. There's no processing done to it. It's mainly the stuff which is only for experts and often not given to users. No one can use with it. It's some ground processing done, and then we have the so-called level 1 data, which are the physical measurements at the satellite where it's measured. So this is typically some radiance, some electromagnetic intensity, which is measured on top of the atmosphere. Then there is processing done to the so-called level 2, which are thematic variables at the Earth's surface. It's still in the, let's say, the space and time coordinates as the satellite has measured it, as I showed you in the previous image where we had this long stripe from Sentinel-3. And these thematic variables could be the chlorophyll concentration, for example. If you aggregate this in time and space and you apply a certain map projection, then it is called level 3 data. And if you do further processing, for example, you apply gap filling, you bring it to a regular temporal grid, or you integrate it with models, then it is called level 4. This part here is the domain of the Copernicus space segment. Ideally, they deliver up to level 2, and then the Copernicus services take it and do these more user-friendly products, level 3 and level 4. But there is a seamless transition between from the level 1 to the level 3, and Copernicus services are doing also the level 2 processing where necessary. As I explained for the Sentinel-2, this is not yet part of the space segment, or the ground segment, which is part of it. So this is, let's say, the part of the raw satellites, and then we come to the Copernicus services, which provide these data. And here we have an atmosphere, a marine, land, a climate change, security, and emergency service. And I will talk a little bit more about these services where it is relevant for water quality. So surprisingly, let's start with the land. The Copernicus Global Land Service contains lake water quality, which is provided. Actually, even though this is given by Copernicus, European Union is doing this, but in the background there is always a team of experts doing this. And the lake water quality is actually coming from UK. It's processed physically in Plymouth by PML, and we are working with the colleagues there. My colleague here, Kerstin Stelzer, is doing this, and Stefan Siemes, who talks later, is, let's say, the PI and the man behind the processing and the products. And this lake water quality service done by Copernicus provides for a very large number of lakes globally, quite large variety of products. They come at a spatial resolution of 300 meters, so driven by Sentinel-3 Olchi at 1 kilometer resolution, and there is demonstration products at 100-meter resolution coming from Sentinel-2. There are 10-day products for water, lake surface, water temperature, turbidity, and a trophic state index, which is kind of chlorophyll. And they also provide reflectances. The time span is a long time series going back to the times of Envisat from MERIS and ATSR for the temperature, in 2016 when Olchi was launched to ongoing. The products are available 3 days after the, let's say, period when it is acquired. And this is operational for the 300 meter and, as I said, demonstration products for the 100 meter. When you go to the website of the Copernicus Land Service, they're easily accessible via product portal and by FTP, and there is information about algorithms, quality, and so on. So quite easy to find that. It's, as I said, it's more than 4,000 lakes, most of those in North America and Europe, as you can see here. And what may be of interest is how many UK waters. Not so many yet, but still something. Since you get the slides, you can see it, but the table you can see on the right side is taken from an Excel table, which is available from that website, which I just showed you. And if you take these products, it's actually a global product. And if you look in a specific lake you're interested, like Lake Balaton, and the turbidity, and then you can see this time sequence here from May to August 2018. Who of you are familiar with Lake Balaton can see that we have these different parts in the lakes, one which is quite turbid, the other one which is rather clear, and then you can see how these different domains develop over the time. So that's the type of product that you can get from there. The second service I want to briefly introduce is the marine service. called CMEMS, Copernicus Marine Environmental Monitoring Service. This is working globally on the one hand, and then on 6 regional seas: Arctic, Baltic, Northwestern Shelf, Iberian, Mediterranean, and Black Sea. It provides chlorophyll A concentration and optical water properties, reflectances, light attenuation, absorption coefficient. As I explained, there are level 3, level 4 products, so it's daily means in 1 and 4 kilometer, and a service which is just being set up and will start in January next year is a 100-meter based product on the coastal zone based on Sentinel-2. So that's coming soon. And this also includes a level 4 product, which is a gap-filled 1 daily means and monthly means. Also both in 1 kilometer, 4 kilometer, and from January next year in 100 meter of February. So this is how the things look a little bit like. This is the North Sea, and we have the low resolution 1 kilometer product on the left side, and then the new high resolution product in 100 meter. And they fit nicely together. It's the same type of parameters. It's of course different input data, dedicated algorithms, so they will differ in detail, but overall there is some consistency between the products where possible. As you can see in this example, which is a cutout from the previous scene. So the last one very quickly is the climate change service. The climate change service is really looking at long-term data records which have climate quality. So the idea is in the long time series to detect changes which can be then related to effects, anthropogenic effects or natural variability. But it's important to work across all the sensors available and to align them so that the time series get interpretable. And this is an example. The ocean color product is globally daily. It's level 3 daily maps with a global extent at 4 kilometer resolution, going back to 1997 until present time. All this development work was actually done in an ESA project, Ocean Color CCI, which is led by PML, and we are contributing to this. It's still ongoing, and once the algorithms are matured, they are handed over to Copernicus Climate Change Initiative to then continue the long time series. So in addition to those Copernicus services, which are, let's say, trying to have a general applicable product portfolio, there is also the downstream services, which are providing on individual user requests data, specialized data. And one I would like to show here is a Cyano alert. I'm showing it because we are doing it, so a little bit of advertisement must be. So this is for those of you who are familiar with cyanobacteria. They can be toxic. And just recently it went to the news that there is a mystery of elephants' death, which may be caused by cyanobacteria, but it's known also that other animals die from it, and also for human beings they can be toxic. So this is again the Danube Delta, and then with a dedicated algorithm, cyanobacteria can be flagged, can be identified, combined with the chlorophyll concentration, and then systematically given to the monitoring agencies or institutions working there. Or another example which is done in this is using Sentinel-2 and Sentinel-3 together. This is from August 2018, same area, the Sentinel-2, and this is how it looks like in Sentinel-3. If you have comparable algorithms and work on this, and then you have a nicely combined product. Second example for such a downstream service for local authorities. This is my hometown, is Hamburg, and there it's for the city. The River Elbe is very important. The monitoring is done by regular monitoring stations and cruises. Even though it's a river, the cruises cost a lot of money, and this can be and will be complemented by chlorophyll concentration, which can be derived from Sentinel-2. And if you just compare these two, which are only a few days apart, The lower one is the same classification done as the upper one from the in situ data, but there is quite a bit of cost saving in collecting the data from the upper compared to the lower part. So since I still have a few minutes time, I want to give you a little bit of background, those who don't know it. So watercolor, that's what we're looking at, and this is how a lake looks like, and the guy who's swimming there is me. This was last year in Norway. It was pretty cold, but it was very nice and had a very nice color. And actually looking at the satellite image Sentinel-2 from the same day, this was the lake where you saw me. And these are all different lakes around. This is the mountain there, and these are all different lakes, and they have completely different color. And this is the signal we are interpreting when we deduce what is in the water. So looking spectrally, this is again these lakes, and I put some place marks here. And this is how the spectrum, which is measured by the satellite Sentinel-2 in this case. This is the spectrum from the UV blue part, and then the green part, the red part, and here we go to the near infrared. And you can see that we have quite different spectral shapes and also orders of magnitude that we have. But remember, this is measured top of atmosphere, and we need to get down towards at the surface. So a little bit different color, but the same principle. These are just examples how different this color from blue to green to brown can be. And this is caused by the stuff which is in the water. And this is really mostly pretty small. We have dissolved particles, humid acids, which can cause brown color. Also, this is sedum also called, which is in boreal lakes, quite an important driver. And then we come to phytoplankton. The chlorophyll in the phytoplankton is what we can see. When it comes to zooplankton, we don't see it. They don't change the color. But we have terrigenous suspended matter, and eroded mud and sand, and they cause this yellowish. This one is making the color green. And this comes because all these particles have specific absorption and scattering properties. That's what is changing the color. And here you can see if we have plants, phytoplankton, they have different pigments. And the chlorophyll A is the one which is dominating in very many of these plants. And this has significant absorption peaks here in the blue and another one here in the red. But this one is actually which is making the color green. This is absorption. If you have a lot of chlorophyll, it's taking away the blue color, and what's remaining is the green one. And these are the effects we are exploiting when we interpret the measured signal in order to then say how much chlorophyll is there or how much suspended matter is there. So that's really the principle. We have the light coming in here, and this is a little bit of water, and we have phytoplankton, suspended matter, sedum in there. And then we have loss of light by absorption, spectrally modulating our signal. And we have also loss by scattering. These particles scatter, and they do it differently. The phytoplankton is mainly absorbing, also scattering a bit. The suspended matters are mainly scattering. And this is modifying the light. So the incoming and the outcoming, and by looking at the difference in this over a spectrum, we can deduce what's in there. All right, I don't go into this detail. But just one word of cautious, which is sometimes forgotten. This is what we measure. This is this absorption, or this is what, let's say, is modifying our light. And this absorption is related to the chlorophyll A concentration, which is a mass which is in units of micrograms per liter. So it's a mass concentration of the particles. And there is some natural variability between the optical effect and the mass concentration. And there is no way to avoid this uncertainty, because this is what we measure, but sometimes the same absorption relates to a lower concentration, to a lower or higher concentration. So basically this is, I mean, this is a log scale. This is on average, this is something like a factor of 2. That we have between optical properties and mass concentration. So just to keep it in mind. So if we have these different particles in the water, they modify our water. These curves are now reflectances, or not the absorption. It's, let's say, the effect of absorption and scattering. And this is what the satellite, let's say, sees, or we see it with our eye. And if we have a water like this one here, which is west of Lanai, Hawaii, it's pretty clear water. And you can see we have a lot of reflection in the blue part. So it's blue water, and then it's almost nothing here in the red infrared. So this is true blue water. On the contrary, if we look at this one, this blue curve, maybe the colors are not very well chosen. This is Alabama coast, and you can see that we have much less reflectance in the blue-green part. So there is a lot of phytoplankton in that water. There may be a lot of sedum, as well. So this is a spectrum as it looks like when we have very, very turbid due to phytoplankton and sedum absorption. And all these other different shapes, this one is a plankton bloom. We have a peak here and a peak here because we have absorption here and here. This is how we, in brackets, the algorithms, interpret the signal. Just to tell you how complicated it is, we do not only have the water. I was just talking about the water. There is a lot of atmosphere with a lot of complicated things above it. It's air molecules, cloud, aerosol. This needs to be corrected because what we see top of atmosphere is the sum of these things, the water, the radiance which comes from the water, the radiance which comes from the aerosols in the atmosphere, and the air molecules. So this one is, let's say, our noise. We are not interested, other people are. We just are after this one here. And if you look at the relative contributions, we have this 100% of our signal, and this is composed here in the blue part is about 90% scattering by air molecules, another 10% by the aerosols, and only 10% is the water. And the water signal reaches at max actually this 10–15%, depending how much you have in the water. So this is why it is so difficult to work with these data and get the chlorophyll concentration, for example, right. I think this goes too far. I just wanted to highlight the differences between Sentinel-3 and Sentinel-2. I explained to you that it's not easy, simply speaking, and you need the spectral information to resolve these differences in the spectra. So again, we have the spectrum here, and then we have the location of the different bands of Sentinel-2. We have it here at 10 meter, a blue one, a green one, a red one, and one in the near infrared. Some bands here in this one, and then another one in the very blue, and this one in the water vapor absorption. So these bands help us to interpret the signal and to decompose the signal. It's pretty good with the 12 bands, but actually this is how it looks like in Sentinel-3 algae. And as you can see, we have much more bands, and they are all quite narrow as compared to the Sentinel-3 band. And this is really needed to get the small differences in the spectrum, and maybe to go beyond just getting the chlorophyll, but maybe also getting the plant functional types and different phytoplankton species. That's the advantage of Sentinel-3. And also to get small variations in magnitude, you need a very high signal to noise ratio, and this is what is provided by Sentinel-3 algae. Okay, so this was my little theory part, and now I think you understand when you have a top of atmosphere signal, you have a mixture of atmosphere and what's on the water surface, like glint and all the mixtures in the water. After the atmospheric correction, you just get the water leaving reflectance. So you see we got rid of this glint and the aerosols which might be there, and then we see the different colors actually in the water, and this can be interpreted, and you have the suspended matter concentration with very high values here. You have the yellow substance absorption, which is almost zero in the middle, but quite high here, and also in, I forgot the name here. And then when it comes to chlorophyll, we have the plankton bloom here, or the high concentrations in front of the Danube Delta. Right, so to conclude my talks, I have 3 slides on what's next in Copernicus. This was what I was talking about, the current satellites and the services based on this. And what's currently under development is a set of Sentinel expansion satellites, and this gives us opportunities for new products in the future. And then later this decade, there will be the Sentinel next generation types of satellites. We had the A, B, C, and D types of satellites, which we have right now. And ESA and Commission are currently thinking, how can the others be done? The next generation, how should it change? So, but first let's talk about the Sentinel expansions, because they will come. There will be an anthropogenic CO2 mission, a polar ice and snow topography mission, both addressing climate change. There is a passive microwave imager for sea surface temperature and sea ice concentrations coming, a high resolution land surface temperature, and actually this also will give us lake water surface temperature. Hyperspectral imaging, it's dedicated to agriculture management, food security, and mineral resources, but this will also be useful for water, I believe. And then an L-band SAR for soil, vegetation, food security, and ground motion. So this is the full picture. I don't expect that you understand this quickly, but we are currently here, 2020. We have the Sentinel-1, 2, and 3 in space, the 2 satellites, and the C and D models come whenever they are needed or as soon as possible. The 21C, Sentinel-3C, I think is now, they think about 23 even, if I am not mistaken. So there is some change currently under discussion, but that's what's planned. And then we have the 4 and 5, and here we have the expansion series, Sentinel 7, 8, 9, 10. These are the CO2 and temperature and so on, which I was talking about, coming mid of the 2020s, let's say, and the next generation towards the end of the decade. This will be continuation of Sentinel 2, Sentinel 3 in some way, but for example, the altimeter that looks quite clear will be on an own platform, and the optical instruments will be on a separate platform. So, but there is a lot of discussion going on. So to conclude my talk, Copernicus program is European response to global needs to manage the environment, mitigate the effect of climate change, and to ensure civil security. Copernicus space segment consists of a growing fleet of Sentinel satellites, complemented by contributing missions. Sentinel 2 and 3 are the ones providing data for water quality monitoring. I think also 5P, but I must say I'm not an expert on this, but I should have included it. I forgot. Sorry for that. Copernicus services built on the data from the space segment and to provide fit for purpose for high-level product. Land monitoring service, marine monitoring service, climate change service deliver data from inland, coastal, and oceanic waters. We will have a talk later, if I'm not mistaken, by Steve Groom, talking about the need for optimization and harmonization across the different services. That's a European project he's leading, which is quite important, I believe. And then finally, downstream services start from the Sentinels as well as the services data, combine these with additional data and provide tailor-made water quality services for public and private customers. So with this, I finished. Thank you very much.
Excellent. Thank you very much, Karsten. That was a really fantastic introduction and overview and has really set the scene for the rest of the talk. So thank you. Brilliant. Okay, I'm just going to share my screen again, and we are now going to take any questions that you have been sending in the audience via Meeting Pulse. If any other speakers or experts in the audience would like to comment or add anything to any of the questions, please let us know via the chat function in GoToMeeting, and we will try and bring you in. I will now hand over to my colleague Paula to see what questions we have.
Right, okay, I'm going to go to Karsten for the first question. We'll see if we can get Christine back. I think our most popular question then is, will Sentinel-2 Level 2 products for water applications become available in the future?
Well, I can only say what I believe. Someone from European Space Agency can give you a more reliable answer. I think so. As far as I know, they are thinking about it. they started with a level 1 product only, and there was, in the very beginning, there was no plan really to have a level 2 product at all. And then they saw that there is a big need for a standard level 2 product provided by the ground segment. And since this is a land mission, they selected a processing system, Sentinels, which is excellent for land applications, but not really dedicated to water applications. So, and since there is such a big uptake of Sentinel-2 for inland waters, when you go to the conferences, there are as many talks on inland waters as there is on forestry and food together, I think. They are now considering to have a dedicated processing for water. This may just go to the water reflectances, not necessarily to the chlorophyll. But if you have the atmospheric correction right, the second step is a bit more easy. But on the same time, it's more difficult if you talk about inland waters because they are so complex, so different. So that's what I can say to this. Yes, there is ongoing discussion, but I don't know further confirmed plans.
Okay, well, thank you very much. And just to follow up on that, we've just had a comment in the chat from Stefan Simis at Plymouth Marine Laboratory, who says he's available during this session if there's any questions about the Copernicus Land Monitoring Service water quality products, because they're produced by Brockman Consult in partnership with Plymouth Marine Laboratory. If you have questions about that, and we can call Stefan in to answer those. I've got another question for Karsten, actually, which is top of the list with 6 votes. Are the Copernicus products and services used widely within the public sector, or are they mostly used for research? I would add, obviously, the public sector does do some research, but I think this is saying, are they mainly used for kind of a proof of concept academic research, or are they starting to be used operationally for public sector applications?
I mean, quite clear for both. Since I'm more connected to, let's say, the academic and development side and companies who are producing these services, I can say that it's a big uptake by the academic sector. I know from our customers that they need these products, that they are using it, and that there is a use. For example, by our national monitoring agencies, they use it systematically, the Sentinel-3, for the North Sea. There is currently discussion by OSPAR to take it, but I must say I don't really have the big overview. I'm sure there is information about this in the European Commission, and maybe Stefan knows more about the uptake of the Cyglops products.
Thank you, Karsten. I would just mention that earlier this year we delivered Copernicus data through to UNEP, who have been disseminating this information to all countries for the Sustainable Development Goals 6.3 stock take. So actually every country's representatives to that effort have now received Copernicus data. And many questions have been coming through from them, mostly positive, some quite technical as well. So I think there is clear progress that this is now seen as an important source of information.
Okay, thank you very much, Stefan and Karsten as well. And of course, that is part of the aim of this workshop, is to increase public sector use of the Copernicus data products and services. So please do keep questions coming in about that, and also use the ideas panel and meeting pulse to post, what's your priority application, how would you like to use the products, and hopefully we'll get some actions out of this workshop. Thank you. Christine is now back with us, so I'm just going to, and we had a question for Christine about the policy context, which was, are all of these policies and protections effective in sustaining our aquatic and marine environments? So we have all this legislation on the horrendogram. Is it doing its job?
I think that would be a politically sensitive question to answer. I'll speak from my personal viewpoint of what I know, and the answer is no.
Well, that was a very honest and brief answer.
Well, I mean, I'm sure whoever asked the question knows quite well that a lot of things are declining. However, having said that, I was very, very impressed to see the result of the European Wastewater Directive. I saw a presentation about freshwater biodiversity in urban areas. The Urban Wastewater Directive has made a fantastic difference to biodiversity in those areas. So I think in some cases the answer is definitely yes, but in others it's difficult. I mean, there's a lot of, even if you could control things legally, there's a lot of illegal activity as well. I think it's a very big ask.
Okay, thank you. I think, well, that would be worth following that up with another question which is related to that, if I can find it. So bearing in mind that the legislation is partially effective in some areas, that there are good examples, but overall it's not really doing what it's supposed to do of protecting the marine and freshwater environments. Where do you think satellite Earth observation could make the biggest impact in JNCC's marine and freshwater nature conservation work?
I think a better understanding of the impacts and pressures. I mean, what we're kind of very interested in at the moment is if there is an intervention which will cost money, is that intervention cost effective? In other words, once we start to value our ecosystem using natural capital assets registers and such like, when we value that ecosystem, when we know the value of the ecosystem services, we can show that the interventions are actually cost effective. Now, determining that, yes, there's a lot that Earth remote sensing can do in that from space, because we can look at things like what Karsten's just been talking about, the things like the algal blooms. So if we see a microalgal bloom, then we can start to understand that there is a discharge of nutrients, and we can start to investigate. And I wouldn't be, it would be wrong if I didn't mention the socio-economic side of things. I mean, you can legislate, but if you don't understand people's behaviours, you won't be able to change how they work. So, you know, farmers have particular ways of doing things which are natural to them, and they're very unnatural to do things like organic farming and reducing inputs and so on. So I think we need to understand how behavioural science works in this area as well. So I think it's part of a complex panoply of tools and approaches that will help us to improve the environment.
Okay, thank you. So a very important tool in the box is remote sensing. Okay, thank you. I'm going to go back to Karsten. I've still got more questions coming in. The River Elbe work was fascinating. Many UK rivers are rather smaller than the Elbe though, so is there a limit to monitoring rivers that are below 10 meters wide? Will this improve in the future? So this is a question related to the spatial resolution of satellite imagery. That's a question that's come in from DEFRA.
Yeah, I mean, the answer is quite straightforward. With the current fleet of Sentinels and also with the planned ones, they will not have higher resolution than the 10 meters. The 10 meters actually of Sentinel-2 is only available for a few bands, and you need, for the interpretation of the signal, you need them all. So to some extent, you can work with 20 meters by, let's say, the 60-meter bands, by assuming they're the same for 3x3 pixels. But frankly speaking, 60-meter is a good lower boundary to get really high quality information. There are commercial satellites like the Planet Dove, the Rapid Eye, but they have less spectral information, but you can do something with it, and this goes down to a meter. But then the data have to be paid for, and then on top comes the processing, and with less, let's say, with higher uncertainty.
Thank you. And that reminds me that there is a question for Christine that's sort of slightly related to that. So I'm just going to try to find that. So regarding the project you told us about, I think it was in Ireland, detecting green algal blooms. You mentioned that Planet data was used for that, which Karsten has just mentioned. So it was started with Landsat and went on to use Sentinel-2, but it used Planet. Was that because high spatial and/or temporal resolution was needed, or did the freely available Landsat or Sentinel-2 gate data give similarly useful results? And I think, yes, I suppose I would add to this person's question what Karsten just said. It has lower spectral resolution, but so was it still okay for detecting the green algae?
Okay, so obviously that's not my project. I'm only on the steering committee of the project. But what they did say was that they've also, this year, they've been able to get some expensive commercial, very high resolution data. So they're collecting that as fast as they can, because obviously both the getting good spectral data as well as getting some good spatial resolution are both really important for them. And this is a great project, by the way, which I've advertised. I'll have to tell Liam I've advertised it now. But they are marrying that up with the Environmental Protection Agency's water quality data, but they can also do things like look at the number of cows in that catchment area through the agricultural. So they can actually take a view using a view from space, but they can also match that up with ground-based data.
Okay, thank you very much. I'm going to just mention something now, because we've had a question regarding data to access services and products from Copernicus and how that relates to the UK's membership of the EU. And we're going to skip that question for now. We're going to deal with it tomorrow. So just so people who've asked that question or upvoted it, we're going to deal with it tomorrow as part of the discussions with the DEFRA Earth Observation Centre of Excellence. So we'll go over that one. I've got another question now for Karsten. How is suspended sediment distinguished from shallow muddy banks? The area between Essex and Denmark is very shallow, and the bottom of the ocean often shows in the imagery. So I can imagine there would be quite a lot of confusion between the two. Yeah, so how do you distinguish turbidity from the seabed when it's shallow? Good question.
Yeah, well, first I was surprised. I mean, the area between Essex and Denmark is the width of the North Sea, isn't it? It's quite a bit. And on average, there is the Dogger Bank in between, which is quite shallow, but maybe that's why. Anyway, so to answer this, if we see the bottom, it is very difficult to calculate the water constituents correctly because, as it said, you see the bottom and it has the same spectral signature. So most of the algorithms work under the assumption that you don't see the bottom, which is in most of the cases true. Even if you have something like 20-meter water depth and you have suspended sediments in the water, you don't see the bottom. You can make a test, put your feet in the water, and after a certain while, in particular in the North Sea, you don't see it. In particular, if it's muddy. When I go to my North Sea coast here, I can't see it when it's up to my hip or something. However, for example, for inland waters, which can be quite clear, we mask the area where the bottom is seen. There are algorithms, and then you have to know that you see the bottom, and you should have a good idea of how deep it is. Then you can differentiate it. And there are also algorithms who derive the water depth. But at a certain time, you have to make assumptions. You can't do each and everything with highest priority. I would say between Essex and Denmark, most of the area, I would believe what I get with my assumption, which is called actually optically deep, that I don't see the bottom.
Okay, thank you. Yeah, I was interested in that question as well, because we have had the opposite problem. We were trying to detect the seabed through the water column to detect the crests of sandbanks, and then finding that turbidity gets in the way. So it's sort of the opposite problem to that.
One man's noise is one woman's noise is the other one's signal. As I said, if you make assumptions, you can do it. Yeah, and there are also algorithms who do it all together, and then it goes to the uncertainty. But as I said, the easiest is to assume optically deep. Of course, if you're interested and you have an idea of the water depth and you make assumptions on the concentration in the water, then you can deduce something on the sediment or on what's in the water on the ground.
Which thank you very much. And that reminds me, and also what Christine said before, talking about ground truth data. We did have a question about whether, so Karsten, you told us about these new Copernicus missions that are in the pipeline. Is any new ground data collection planned to complement these new satellite missions, for example, to aid validation and interpretation of the data? And I suppose the continuation from that is or do we have what we need in terms of things like temperature?
Yeah, I mean there is the there is the in situ component. In the past, they have mainly coordinated existing activities at a database of meta information where it's available what, including H2020 research data and let's say nationally collected. As part of the new what is it called, the financial program of the European Union, this is currently being discussed. There is also the money for Copernicus, and then it's under discussion now how it's being used. And there is also discussion what's going on in the in situ component. But I haven't heard any precise plans that collection of data will be part of the in situ activities. But I must say this is not my special area. I mean, I know the names who to ask if there is. I don't think there's someone here in the call, but in EA, they are in the European Environmental Agency. They are the entrusted entity to take care of the in situ activities. Maybe in the next program it might be.
And we will be reporting these questions and answers to them in our workshop report that we'll write up and put on the website. So if we might come back to you for information on things like that. Just so you may have seen in the chat, everyone, but Christine has had to leave now for another appointment. We had a question which I didn't get time to ask to Christine, which was about what type of Earth observation data was used in UKCMAP. But we have a talk coming up in the next session, which is from Michael Vasquez from IFRAMER about seabed habitat mapping. So that may be something we're able to cover then. It was what type of Earth observation data was used in UKCMAP, what technique was applied, and what software was used. So that may well be something that we can cover in the next session. We've got just 5 minutes to go before we take a break. So I'll go through another couple of questions if I can. So Karsten, I've had a question. What variables are likely to be available in the 100 meter by 100 meter resolution coastal products you mentioned for release next year?
Yeah, I mean, this is quite well defined. It's the remote sensing reflectance, so the spectrum after the atmospheric correction, and then turbidity, chlorophyll, and backscatter coefficient.
Okay, brilliant, thank you. This is hopefully, I don't know if this will be an easy question or not, but do you know how many people currently use? Sorry.
I just get someone is telling me, you forgot to say is also suspended sediment. Sorry, I forgot
right, and
suspended sediment as well. Thank you, Carol.
Thank you. Yeah, do you know how many people currently use the Copernicus services?
No, I don't know the numbers. I know that the uptake of data is really huge, and people from the Commission, they show these graphs which are increasing over time quite significantly. This is download. I mean, there are the success stories where people say what they do with it, but these are, let's say, individual success stories, like Stefan just reminded me from the UNEP example. But in terms of numbers, I'm sorry, I don't know that. But it is used because I don't believe otherwise it would be continued and even increased.
Like, I suppose there's different ways of accessing the data as well, and different data gets processed in different ways and then available through different channels. So may be hard to have absolute metrics on it. Are there any, you may have touched on this in your final 3 slides, but are there any future products or services that may revolutionize the use of EO for water quality monitoring?
No, I haven't touched upon this. Well, what's revolutionizing?
Revolutionize, yeah.
Yeah. I mean, there is quite some activities to get the phytoplankton composition, and our colleagues in PML are quite good in this. And the Sentinel 5P, which I forgot in my, well, not forgot, because which I didn't touch upon so much. This is providing spectral information, which I believe is quite useful for this. I know that Shuba, she's on the call here, she is quite experienced on this. So I would say this will make quite an important difference if we can better distinguish the different phytoplankton species. Mm-hmm. And secondly, from the missions, the high-resolution temporal sensor. This is not directly water quality in the more narrow sense, but if you look outside the Earth observation domain, water quality contains a lot of parameters, including also temperature, if I'm not mistaken. And this, to get this, I think LTSM will be at 100 meter, will make quite a difference compared to the roughly 1 kilometer which we have right now. And there are many people interested in lake water temperature.
Okay. Well, thank you very much. We're just coming up on past, so we will be going to a break soon. I'll just ask one more question, if I may. How do top of atmosphere images impact Earth observation time series analysis, for example, in a time series analysis of ocean color?
Yeah, I saw this question. I'm afraid I don't understand. I mean, we need top of atmosphere images that the input to everything. I can't see it actually on the slide anymore. I must say I don't understand the question. I'm sorry.
Oh, I'm sorry. And unfortunately, with this way of asking questions, we can't really ask for clarification. It might be something that we can come back to. Yes. If they put into the chat. I'm just going to check something. We had the question earlier regarding the number of users for the Copernicus services. And we've had a reply from John Hicks and DEFRA Centre of Excellence, says that user numbers of the services are constantly increasing in line with the maturation of services and promotional activities. And some services are more widely used than others. So CMEMS has a lot of users compared to CLMS. Okay, so just to add to that.
The first one is the marine service has a lot of more users compared to the land monitoring service.
Land monitoring. Yeah.
So thanks, Jonathan, for helping me with this.
Yeah, thank you very much. Okay, I think we'll have to leave it there because we're going to go into a break. And Emily, if you're able to just move on to the next slide so that we've got to let people know that we're coming back soon and that it's got the links about and what the next session is. So we're going to take a break until 2:45, so a 15-minute break. Okay.